This video is going to show you how to combine conservation of energy and the work done by non-conservative forces in solving a problem. An 88-kilogram skydiver drops out of a plane and free falls for 404 meters before opening his parachute. As he falls, he feels an average resistive force of 550 newtons. How fast is he moving when his parachute opens up? Use energy methods to solve. So, he drops out of an airplane. He falls 404 meters to where his parachute opens up. I'm going to call this height 0 because that's basically the bottom part of the motion that I'm looking at. During this whole time he falls, there is a resistive force of 555 newtons. So this resistive force is really drag or air resistance, and it's a non-conservative force. In other words, whatever it does, whatever energy it uses up, you don't get it back. It's all gone. Only gravity and springs give us our conservative forces. So when I'm setting up, I'll look at conserving all the mechanical energy from when he dropped, and then because the force opposes the motion he's moving in, that force is removing energy that he started with. So as he falls, this resistive force of 555 newtons is removing energy. In other words, it's doing work against the guy, or work on him as he falls. So I'm going to put minus W on the left-hand side. So I start with a certain amount of energy at the top, and then I lose energy as he falls. Now I need another place to compare to, so I'm going to compare the other place as when the parachute opens, since the question asks how fast he's moving when it opens. So all this is equal to the sum of all the mechanical energy where the parachute opens at the bottom of his motion. Now I'll start looking at the energies. When he drops, what I'm going to do is I'm going to look at the kinetic energy he has at the top and the potential energy due to gravity. Then I'll subtract out the work that happens, because that's removing energy from what he started with, and that's going to leave me with energy left over of kinetic and potential. Now what I'm going to do is I'm going to go through and I'm going to figure out which ones I have by asking a couple questions. First, I'm going to ask, is he moving at this location? In other words, when he dropped at the top, is he moving at the top? And he's not, because it says he dropped. So that means initial velocity is 0, so that gets rid of the kinetic energy. Next question I'm going to ask is he above the other location? In other words, when I'm looking at the moment when he drops out of the airplane, is he above the other location when the parachute opens? And he is. So he has height above the other location, so he has potential energy due to gravity. I'll leave the work alone and move on to the kinetic energy on the right-hand side when the parachute opens. Is he moving at this location? That is where the parachute opens. And he is, I think. So I'll keep the kinetic energy in my equation. Is he above the other location's height? And in this case, he's not. He's at the lowest of the two locations that I'm comparing. So I'm going to get rid of that energy, because the height's going to be 0 right there. So now I have my equation. I've just created it. I'm going to have mgh due to gravity, that's potential energy due to gravity, minus the work done by the non-conservative force of the air resistance. That's all going to equal to is kinetic energy at the bottom of this motion that I'm considering. So I'll take my numbers and plug them all in, as you can see here. And velocity is the only unknown I have, so I'll solve it for v squared and get the final velocity to be 53.1 meters per second.